Natural gas leaving the reservoir is rarely ready for sale or transportation. It often contains water, hydrogen sulfide, carbon dioxide, heavy hydrocarbons, and other contaminants that can create operational, safety, and environmental challenges. Gas treatment is the collection of processes used to remove these contaminants and transform raw gas into a pipeline-quality product. Throughout this chapter, we will examine dehydration, sweetening, sulfur recovery, and other treatment technologies that allow engineers to deliver safe and reliable gas to customers. By the end of this chapter, you will understand not only how these systems work, but also how engineers select the right treatment technology for a specific field application. If natural gas is not properly treated, it can create significant operational and economic problems. Water can lead to hydrate formation and corrosion. Hydrogen sulfide introduces serious toxicity and safety concerns. Carbon dioxide reduces gas quality and accelerates corrosion, while heavy hydrocarbons can condense and create transportation issues. Gas treatment removes these unwanted components before the gas enters pipelines, processing facilities, or end-user markets. In simple terms, treatment converts a problematic fluid into a valuable energy product. Natural gas is rarely pure methane. Most gas streams contain a variety of contaminants that affect processing, transportation, and product quality. Water promotes hydrate formation. Hydrogen sulfide creates toxicity and corrosion concerns. Carbon dioxide lowers heating value and contributes to corrosion. Heavy hydrocarbons affect dew point specifications, while mercury can damage critical cryogenic equipment. Understanding the contaminants present in a gas stream is the first step towards selecting the appropriate treatment process. The impact of gas contaminants extends far beyond product quality. Even small concentrations can have significant consequences. Hydrogen sulfide threatens personnel safety, while carbon dioxide and water accelerate corrosion throughout the production system. Water can also trigger hydrate formation, creating restrictions or complete blockages in pipelines. These technical problems ultimately become business problems through downtime, production losses, maintenance costs, and reduced reliability. This is why gas treatment is considered a critical part of modern gas processing operations. Every gas field tells a different story. Some contain water that forms hydrates, others contain hydrogen sulfide, carbon dioxide, or valuable heavier hydrocarbons that can be recovered for additional revenue. The challenge for engineers is identifying these contaminants and selecting the right treatment technologies to remove them efficiently. This gas treatment roadmap follows the journey of natural gas from the wellhead to pipeline quality sales gas. Through separation, dehydration, sweetening, sulfur recovery, and dew point control, contaminants are systematically removed, equipment is protected, emissions are reduced, and product value is maximized. The key message is simple: there is no universal treatment solution. The right process depends on the gas composition, product specifications, and project economics. Successful gas treatment delivers what every operator wants: safe operations, reliable facilities, environmental compliance, and profitable gas production. Water is one of the most common contaminants in natural gas and one of the most problematic. If left untreated, water can form hydrates, accelerate corrosion, and cause gas streams to fail pipeline specifications. The purpose of gas dehydration is to remove water vapor and produce a dry gas stream suitable for transportation and processing. Several technologies are available, including glycol dehydration and solid desiccant systems. The choice depends largely on the required gas dew point and operating conditions. The heart of a TEG dehydration system is the contactor tower. Wet gas enters from the bottom while lean glycol enters from the top, creating countercurrent flow. As the gas rises through the tower, water vapor transfers into the glycol because glycol has a strong affinity for water. The gas leaves the top of the tower significantly drier, while the glycol leaves the bottom carrying the absorbed water. The effectiveness of dehydration depends on pressure, temperature, contact area, and glycol purity. After absorbing water in the contactor, the glycol becomes rich glycol and must be regenerated before it can be reused. The rich glycol passes through a heat exchanger and enters a reboiler where heat drives off the absorbed water. The regenerated lean glycol is then cooled and recycled back to the contactor. This regeneration loop allows the glycol to be reused continuously, making TEG dehydration one of the most economical and widely used gas treatment processes. When extremely dry gas is required, solid desiccant systems are often selected instead of glycol dehydration. These systems use materials such as molecular sieves to adsorb water directly onto a solid surface. While one vessel removes water from the gas stream, the second vessel is regenerated using heated gas. The vessels periodically switch roles to provide continuous operation. Because they achieve extremely low water contents, molecular sieve systems are commonly used in LNG, cryogenic, and specialty gas applications. No dehydration technology is ideal for every application. The selection process begins with the required gas dew point. For most pipeline applications, TEG dehydration provides an economical and reliable solution. However, when ultra-low water content is required, such as in LNG facilities, molecular sieve systems become the preferred choice. Engineers must balance technical requirements with economics, considering gas flow rate, operating conditions, capital cost, operating cost, and long-term reliability. After water removal, the next major gas treatment challenge is acid gas removal. Gas streams containing hydrogen sulfide or carbon dioxide are known as sour gas streams. Hydrogen sulfide is highly toxic and corrosive, while carbon dioxide reduces heating value and contributes to corrosion problems. Gas sweetening removes these acid gases and produces a safer, higher quality gas suitable for transportation and sale. Hydrogen sulfide and carbon dioxide are among the most important contaminants in natural gas processing. Hydrogen sulfide presents serious safety hazards because even small concentrations can be dangerous to personnel. Carbon dioxide, while not toxic at typical concentrations, lowers gas quality and contributes to corrosion. Removing these components improves safety, protects assets, and ensures compliance with pipeline and environmental specifications. The most widely used gas sweetening technology is amine treatment. The process begins in the absorber, where sour gas flows upward while lean amine flows downward. As the gas contacts the amine solution, hydrogen sulfide and carbon dioxide are absorbed into the liquid phase. The sweet gas exits the top of the absorber, while the rich amine leaves the bottom carrying the absorbed acid gases. The rich amine is then regenerated by heating it in a stripper or regenerator. This releases the acid gases and restores the amine for reuse. The regenerated lean amine is recycled back to the absorber, creating a continuous treatment cycle. Not all amines behave the same way. Different amines are selected depending on gas composition and treatment objectives. MEA is highly reactive and effective for acid gas removal, but it requires more regeneration energy. DEA provides a balance between performance and operating cost. MDEA is widely used because of its selectivity for hydrogen sulfide and lower energy consumption. DGA is often selected for specialized deep sweetening applications. Choosing the right amine can significantly impact both plant performance and operating economics. The absorber is the heart of the amine sweetening system. Sour gas enters from the bottom while lean amine enters from the top. As the fluids flow countercurrently, acid gases transfer from the gas phase into the amine solution. This mass transfer process produces sweet gas at the top of the tower and rich amine at the bottom. The effectiveness of sweetening depends on operating pressure, temperature, amine concentration, and the amount of contact area available inside the absorber. Removing hydrogen sulfide from natural gas creates another challenge. What do we do with the acid gas that has been removed? The most common solution is sulfur recovery using the Claus process. In this process, hydrogen sulfide is converted into elemental sulfur through a series of thermal and catalytic reactions. Sulfur recovery not only reduces harmful emissions but also converts a waste stream into a valuable industrial product used in fertilizers, chemicals, and manufacturing. The Claus process is the industry standard for sulfur recovery. First, a portion of the hydrogen sulfide is burned in a thermal reactor. The remaining hydrogen sulfide then reacts with sulfur dioxide in catalytic reactors to form elemental sulfur. The sulfur is condensed and collected, while the remaining gas continues through additional recovery stages. Modern sulfur recovery units can achieve recovery efficiencies greater than 95%, with even higher values when combined with tail gas treatment systems. Even after dehydration and sweetening, natural gas may still contain heavy hydrocarbons that can condense during transportation. Hydrocarbon dew point control removes these heavier components by cooling the gas and separating the resulting liquids. This improves pipeline compliance, enhances flow assurance, and often creates valuable liquid hydrocarbon products. In many facilities, dew point control also serves as the first step toward NGL recovery. Natural gas liquids represent an important source of revenue in many gas processing facilities. By separating heavier hydrocarbons such as ethane, propane, butane, and natural gasoline, operators can generate additional products while improving gas quality. NGL recovery transforms what would otherwise remain in the gas stream into valuable products for petrochemical, fuel, and refining markets. Although mercury is typically present only in trace quantities, it can cause serious damage in gas processing facilities, particularly in LNG plants where aluminum heat exchangers are used. Mercury removal units use specialized adsorbents to capture and remove mercury before the gas enters sensitive equipment. This protects critical assets and improves long-term plant reliability. In this worked example, we evaluate a new gas field containing methane, carbon dioxide, hydrogen sulfide, water vapor, and heavier hydrocarbons. Before the gas can be sold, these contaminants must be removed because they can cause corrosion, hydrate formation, safety hazards, and transportation problems. The first step is amine sweetening to remove hydrogen sulfide and carbon dioxide. The gas then passes through a dehydration unit to remove water and prevent hydrates. Next, an NGL recovery unit extracts valuable heavier hydrocarbons such as LPG and condensate. Depending on the facility requirements, mercury removal and final polishing may also be included. The result is clean, dry, sweet gas that meets pipeline specifications and can be safely transported to customers. This example highlights how engineers select the appropriate gas treatment train to improve safety, protect equipment, and maximize the value of produced gas. In this worked example, our objective is to select the most suitable sweetening process for a sour gas stream. The gas is produced at a high pressure of 1,200 psi and contains 15% carbon dioxide and 0.2% hydrogen sulfide. The treatment target is to reduce hydrogen sulfide to less than 4 ppmv and carbon dioxide to less than 2%. The first step is evaluating the feed gas conditions. High operating pressure and high carbon dioxide concentration favor physical absorption processes because they can remove acid gases efficiently with lower energy consumption. Since the hydrogen sulfide concentration is relatively low, a physical solvent can still achieve the required product specifications. Next, we compare the major commercial physical solvent technologies, including Selexol, Purosol, Fluor Solvent, and Rectisol. Key selection criteria include acid gas removal performance, energy requirements, operating costs, and industrial experience. Based on these criteria, Selexol is selected as the preferred process. It performs well at high pressure, provides excellent carbon dioxide removal, requires less regeneration energy than amine systems, and offers lower long-term operating costs. The treated sweet gas then proceeds to downstream dehydration and processing, while the separated acid gas is sent for sulfur recovery or carbon dioxide handling. The key lesson from this example is that successful process selection depends on matching the treatment technology to the gas composition and operating conditions. In this case, Selexol provides the most efficient and economical solution. In this worked example, we investigate a gas processing facility that is experiencing several operational problems. Operators have reported increasing pipeline pressure drop, corrosion in downstream piping, heating value below specification, and liquid hydrocarbon accumulation in the system. The first step is to identify the likely contaminants causing these issues. Water and heavy hydrocarbons can create liquid buildup and increase pressure losses. Hydrogen sulfide, carbon dioxide, and water together create a highly corrosive environment. Carbon dioxide also reduces the heating value of the gas, while heavy hydrocarbons can condense and collect in low points of the process. After matching each symptom to its most likely cause, the next step is selecting the appropriate treatment processes. Sweetening removes hydrogen sulfide and carbon dioxide, dehydration removes water vapor, and NGL recovery removes heavier hydrocarbons. Additional mercury removal may be required depending on the facility design. The recommended gas treatment train consists of sweetening, dehydration, and NGL recovery, producing clean, dry, and specification-compliant sales gas. The key lesson is that operational problems are often symptoms of untreated contaminants, and identifying the root cause allows engineers to select the correct treatment solution and restore reliable plant performance. A modern gas processing facility combines multiple treatment technologies into a single integrated process train. Each unit removes specific contaminants and prepares the gas for the next stage. Together, these systems transform raw reservoir gas into a safe, reliable, and marketable energy product that meets transportation, environmental, and customer specifications. Throughout this chapter, we've seen that gas treatment is much more than contaminant removal. It is a critical engineering discipline that protects people, safeguards equipment, ensures environmental compliance, and maximizes the value of natural gas resources. Whether removing water, acid gases, mercury, or heavy hydrocarbons, every treatment process contributes to the same goal: transforming raw gas into a safe, reliable, and marketable product. The engineering lesson is clear. Understanding contaminants and selecting the right treatment technologies are essential for successful gas processing operations.